Hey, welcome back. We're going to pick up where we left off from the last video, continuing with the cofactors, determinant, and the connection between those two. This problem is kind of a nod towards differential equations, if you've had that or not. If you've had it, you'll recognize some of these types. If not, that's okay. You'll learn them when you take that course. Consider a system in which S is an unspecified parameter. Determine the values of S for which the system has a unique solution. And we're going to use Cramer's rule to describe the solution. Okay, so let's take our system, two equations, two unknowns, with a parameter S involved. The coefficient matrix is going to have the first column is 3S, negative 6. Second column, negative 2S. A sub 1b is when the first column is replaced with vector b. So 4, 1 becomes your first column. Then you have negative 2 and S staying as your second column. A sub 2b, first column is left alone. So we're going to leave that one the same. Second column gets replaced with b, 4, 1. If we view this as a matrix equation, A times X equals B, we want to solve for X. Okay, now let's compute these determinants. The determinant of matrix A is 3S squared minus 12. 3S squared minus 12. Now that will factor as a difference of two squares, so you factor your 3 out, and that becomes 3 times S squared minus 4. The S squared minus 4 will break down into X plus 2, X minus 2. I'm going to take this back off, but I wanted to show that step. So you factor your 3 out, and then this becomes a difference of two squares. And that'll factor further into S plus 2, S minus 2. So this system will have a unique solution as long as S isn't negative 2 or S isn't positive 2. Otherwise, you have a zero determinant. Okay, now let's do Cramer's rule, which we've already made our substitutions up here, and we're going to find the first X value of the solution, the first entry. So it's the determinant of A sub 1b, so that's 4S minus negative 2, that's 4S plus 2, over the determinant of A, which we've just calculated above, 3 times S plus 2, S minus 2. Okay, so that's X1, and that'll go here. That would be your top entry. X sub 2 is determinant of A sub 2b. That's 3S minus negative 24, so 3S plus 24 over the same denominator, because the determinant of matrix A doesn't change. This one can be reduced. If you factor a 3 out of the top, then you have 3 parentheses S plus 8. Those 3's will cancel, so you have S plus 8 over S plus 2 times S minus 2. This and that would be your solution matrix. And it's unique as long as you don't have an S value of negative 2 or positive 2, because that makes your determinant 0. From the previous video, recall matrix A has a lot of entries with row I, column J. The IJ cofactor, we discussed it, is negative 1, and the power is the sum of the row and column times the determinant of the minor matrix left over where row I and column J are ignored. So for example, let's take matrix A. We've got a 3 by 3. The cofactor, the 3, 1 cofactor We have -1 to the 3 plus 1, which is 4. -1 to an even power is +1. If you ignore row 3 and column 1, then these 4 values are the ones you still have. And we're going to take these 4 values, calculate the determinant of them. So that's 36 minus 16 times a +1, that's 20. And then just as another illustration, if we take that 1, 2 cofactor, row 1, column 2, row 1, column 2, it looks like a letter T. 1 plus 2 is 3, so -1 to an odd power is -1. Ignoring row 1, column 2, we have -2, -1, and -9, 0. The determinant of those 4 is the minor is 0 minus 9, -1. 0 minus 9 is -9, but times -1 makes it +9. So that's just an example of how to calculate, again, cofactors. It turns out that we're going to use this pretty heavily on a certain way of doing an inverse of a 3x3, probably on the next slide. We also need to look at a definition. It's called an adjoint. The adjoint of A, denoted ADJ of A, is a matrix that is the transpose of the matrix of cofactors. For example, if the matrix of cofactors from matrix A is this one, I went ahead and calculated all 9 cofactors, but I put a box around 9 and 20. This is the 3, 1 cofactor. We calculated it to be 20. This one is the 1, 2 cofactor, and we calculated it to be 9. So I put boxes around the ones we calculated up here, and then I just, in my own spare time, I calculated the rest of those 7 values. I do want to say that, excuse me, if you look online, there are online matrix calculators. I emailed you a couple of suggestions, and some of them will actually do your cofactor matrix for you if you type in the original. So just be smart when you're working these. But anyway, long story short, if this is a matrix of cofactors, its adjoint will be column 1 becomes row 1 because it's the transpose. Column 2 becomes row 2, and column 3 becomes row 3. Sometimes adjugate is used instead of adjoint. When I was going through undergrad and graduate school, adjoint was what I always heard. This textbook sometimes will break out adjugate on you instead. Just know that they're the same thing for our purposes. Okay, so after going over cofactors and defining adjoint, we can now give a formula for the inverse of A. It's 1 over the determinant times the adjoint. Let's take matrix A. It's a 3x3. Now, I put this in the calculator just to quickly get a determinant of it, and I got 14. The 9 cofactors, and I'm not going to go through all 9 or it'll take 20 minutes just to do it. But anyway, row 1, column 1. You don't use the number, you use the sign, which remember it's a checkerboard, so it's positive, negative, positive, positive, negative, positive, positive, and so forth. If that one's negative, its neighbor's positive. If it's positive, its neighbor's negative. So anyway, long story short, I did put in the plus and the minus just to show you that checkerboard effect. The main diagonal is all positives. But the key to it is getting your sign right, and then for, let's see, row 1, column 1, if you ignore row 1 and column 1, then you calculate the determinant of those 4 entries. If you don't write the word determinant, vertical bars represent the same thing. So if you see this, that represents determinant. Let me randomly pick this one. Cofactor, the 3, 2 cofactor would be row 3, column 2, row 3, column 2. It's like an upside down capital T. 2, 1, 3, 1 are the numbers that remain. Because 3 plus 2 is odd, you have a negative, and then the determinant is 2 minus 3, which is negative 1, but negative 1 makes positive 1. These 9 numbers are your cofactors of matrix A. If you transpose them, in other words, column 1 becomes row 1, column 2, row 2, column 3, row 3, that's your adjoint. Now we calculated the determinant up here in the beginning, so 1 over the determinant of 14, so 1/14 times your adjoint, which is the transpose of your cofactors. Lord, that's a mouthful. Let's look at a couple theorems. If A is a 2 by 2 matrix, the area of the parallelogram determined by the columns of A is the absolute value of the determinant of that 2 by 2 matrix. If A is a 3 by 3 matrix, the volume of the parallelepiped determined by the columns of A is the same thing. It's the absolute value of the determinant of your matrix. Now, if you're given points, and these will form a parallelogram, I'll sketch the original. Given these 4 points, -2, -2, 0, 3, 4, -1, 6, 4, the idea is if one of these original points is not the origin, then you pick one of them, pick one of your 4 points, translate it so that it does fall on the origin. The easiest one for me to spot was -2, -2. I know that if I add 2 to both of these numbers, I force it to go to 0. So that's what I do. 0, 3, if you add 2 to both numbers, it's 2, 5. Add 2 to both numbers, that's 8, 6. Add 2 to both numbers, that's 6, 1. Once you've translated your parallelogram to where one vertex is on the origin, then the 2 vectors leading out, or at least the 2 sides, after translating, we have 2, 5 and 6, 1. That one's the sum of them, don't worry about it. 2, 5, and 6, 1. If you make those your columns of A, the translated parallelogram is determined by the columns of A, which are your new points leading away from the origin. 2, 5, 6, 1. 2, 5, 6, 1. And then you calculate the determinant. 2 minus 30, it's -28, but you take the absolute value, you get positive 28. Don't forget the absolute value of the determinant. And then an example for a linear transformation, let S be the parallelogram determined by the vectors B1 and B2, and we're going to let matrix A be this 2 by 2. Compute the area of the image of S under the mapping of X is translated by A times X. So we've got a linear transformation example. Basically, that previous slide where we moved the parallelogram over to where one vertex hits the origin, it's very similar. The area of S, which is your image, after translation, is we're going to take these 2 vectors leading away from the origin. These are the images, remember? So images are where you land after the transformation. At least in my mind, that's how I interpret it. So anyway, long story short, -2, 3, -2, 5, those become your columns. And I noted here B1, B2. So the absolute value of that determinant, we have -10 minus -6. So -10 plus 6, that's -4. absolute value is positive 4. The determinant of A is 12 minus 9, which is 3. And therefore, the overall area is the absolute value of the determinant of A times the area of S. The area of S is the absolute value of the determinant of your vectors. Determinant of A is 3. Area of image S was 4. So 3 times 4, that gives us 12.